Day one, which speaks about conditional probability. What is conditional probability? It's when we know something has happened, that can change the probability of something else happening. So when we're trying to find the probability that one event will happen under the condition that some other event has already been known to have occurred, then what we are trying to do is what's called a conditional probability. So, for example, if I said to you, what is the probability that a random person in the high school, let's include teachers, students, all this, what's the probability that someone is pregnant at NCUHS? And I mean, I don't know any information about this, but let's say that there's like 800 people, and let's say there's 4 pregnant out there. So I would say 4 out of 800 people, and then that would be whatever the decimal was there. But what if I told you that I'm not going to include any females in this situation? Then what's the probability that your random person is pregnant, given you already know that this person is going to be a male? Now, the way we would write this is we'd say, what's the probability that you're pregnant? And I'm going to make a slash. That slash means this statement of given, and what comes after has to be the thing that's true about everybody I've picked, and that's being male. So what would you tell me the probability is now? Well, nobody. So because I now told you that we're talking about males at North Country, that changes the probability from, and 4, it was a subjective probability. I don't know if that's at all true. Anyway, conditional probability is the probability that one event happens given that another event has already been known to have happened. That's the conditional probability. And so when we look at how do we say this right here? We would say probability of B given A. So it's the probability of B given A. And what does it mean? It means the probability that B is going to occur given that A has already occurred. We have this formula right here to help us solve this, and I'm going to ask you to always expand this formula, expand those givens. This is the given. Expand it out. Because it sometimes will become absolutely necessary to be able to use that expanded form. And how is this formula written on your formula sheet? Look at the front page of your formula sheet in the second part, which is probability. It looks like this. So how does that change the formula above? Now it's just saying the probability of A and B, but it can write it as the intersection, over, so what was down in the bottom is still in the bottom. See how these things are in the bottom? Probability of B. So that's on the formula sheet. Get comfortable with expanding out. We're going to do some problems now on the next page with that. Okay, so these are our pierced ear people. We're going to have no naked answers, meaning I want you to have your notation, writing your symbols. And then we'll try to, hopefully I'll have enough room to write the answers in context. So there's my data. I want to, given that a person with pierced ears is chosen, so that's what's true about them. They have to be someone with pierced ears. What is the probability that the person is male? So probability, think about given is the condition. And sometimes that's easier to identify. So I've identified that you have to have pierced ears. So that's my condition, and it goes on the bottom, and the male would go on the top. So now I'm going to expand it. That's not naked now because I have a notation. Now I'm going to expand my notation. Notice that I have to write my probability twice, that P in the formula. So I need to be a male and pierced, which is the intersection, over being pierced ears. And there are 19 males and pierced, they're right here. And out of 178, because it's a probability, and then pierced ears, there were 103 out of 178. So what you'll notice is in this format, that will always cancel out, but you don't always have a table of data. Sometimes you just have a collection of probabilities. So 19 out of 103, which is 0.184. So the probability of being male given pierced ears is approximately, or estimated to approximately 0.184. Okay, now next one. If a male is chosen from the group, what is the probability that he will have pierced ears? So that's just changing the wording around, and I don't have the word given there. So you have to be able to identify when there's something that has to be true and it's being the male. So like I can see that I'm definitely picking a male. And now I want to know the probability of being pierced. So it's actually slightly different from above because I still have pierced in male in the top, but now I've got being male in the bottom. So that still leaves me with 19 out of 178 in the top, but now for males there are 90 out of 178. So 19 out of 90, that is 0.211. So if a male is chosen, from the group, the probability of pierced ears is 0.211. Estimated to be, wow, that was close. Are the probabilities equal? Why or why not? What happened here? No, they weren't equal. Why? Because the condition was different in the two situations. In the first one, I was picking pierced ears people, and we know that there are more females with pierced ears. And in the second one, I was picking males, and we know that males seem to tend to not have pierced ears. So that we could have answered this using our conditional distributions of gender. It's like, is there a relationship between having one's ears pierced and gender? Well, I could have done that, and what I would have done is looked at based on gender. So the genders would have been our division. And so based on gender, if I'm looking at pierced, for the males, I would have 19 out of 90, and not pierced, it would have been 71 out of 90. That would have been for the males, based on the gender, that being male. And then based on gender being female, I would have had 84 out of 88. See how I'm basing it on female? That's my base. And then there would be 4 out of 88. And then I would have done a graph. That would have been how I would have done this. Probably a stacked bar graph would be the best way to go with this. And I would have ended up with my males being really small, like here. This would be, we could have, this could be pierced, and this would be not. Remember these techniques from chapter 1? So this could be, and then I would, of course, label it. And I would give it a title. And that would show a relationship between the two, that there's a relationship of gender and piercing, because you can see that there's a clear difference between these two filled in bars. This using conditional probabilities, it kind of reminds me a little bit of functions, and looking at composition of functions, it reminds me of this. But anyway, the idea in this is we want to show that having pierced ears, that it won't change if I am a male. And what that would mean is that these things are independent, which is different from being mutually exclusive. Independent means one's not affecting the other. So when you are equal, that would be sign of that. So to prove this, I would want to show, let's see, I gotta extend this. I would want to show that, well, being pierced given that you were a male was 0.211, and having pierced ears is, let's see, there's 103, that's 103 out of 178, which is 0.579. So if they were independent, these two things would be equal, but they are clearly not. They do not equal. So since probability pierced equal to 0.579 does not equal probability pierced given male, these are not independent. So that means we have something that's dependent. And if you did find that these were equal, you actually would need to check that that the male doesn't change. Whoops, male. It's supposed to be male. Given pierced. So like you have to check both directions to see if this holds true as well. So if it fails on either direction, then it's not independent, it's dependent. And so that's why it reminds me of the functions, because like you have to check the composition of functions. Like if that comes out to be x, then you always have to check the other direction too. And then you can say that they're inverses of each other. It kind of reminds me of that. But so anyway, both ways must be equal to be independent. Okay, so next page. That's what that says. So independence is knowing that when one event happens, it's not going to change the likelihood of the next event happening. Things like flipping a coin. and those events would be independent. When two events A and B are independent, then the occurrence of one event is not going to affect the other. And that would mean that your probability of A given B will be the same as A, probability of A, and your probability of B given A will be the same as probability of B, because that condition doesn't change it. You do need to check both ways to be independent. So if we go in here and we try an example, this is going to show us an example where they really are independent. If I'm flipping two coins, given the first flip was heads, what is the probability of tails on the second coin? So if you think about, I'm flipping two coins, just a quick review, how many outcomes would you have? Event 1 was coin 1, event 2 was coin 2. There are going to be 4 ways of this happening. And just to review what a sample space looks like, there's my sample space for that. So given that the first flip was, given that this first flip, so the first was heads, what is the probability of the second being tails? Well, then I'd have probability of second tails and first was heads. I don't know why I put that line there. Over probability first was heads. Okay, let's see. How many of them do you see where the second was a tail and at the same time the first was a heads? There was 1. Out of how many did you see where the first was heads? There were 2. Whoops, 2 out of 4, 1 out of 4, 2 out of 4. The 4s are going to cancel. That makes it a half, 0.5. So you can see that the probability is the same as the probability of getting tails, because getting the second being or probability of tails on the second flip, there were 2 out of 4, so that's a half. Or probability of just getting tails is a half. So yeah, and so as you can see that these two things are the same, and if I were to check probability of heads and check that compared to probability of heads given that tails has already happened, that actually would come out the same too. So it is going to be independent. All right, now we're going to draw cards from a standard deck with no replacement, meaning I'm not going to put the cards back. After I take out a card, one of the cards is out. If I draw 2 cards and I compare the first card is drawn as a king, what's the probability that the second card drawn is the queen? So I want probability second queen given the first was a king. So probability second queen and the first was a king over probability of the first being a king. All right, how do we get the probability of getting the second being a queen and at the same time the first was a king? The easiest way to do something like that is to set up parentheses and just run through it. Here's my first. I want that first one to be a king. There are 4 kings in the deck. There are 52 cards in the deck. Now that I've taken a king out, because there were 4 kings, now there's 1 less of them, but I'm now interested in getting a queen. But what's different is this denominator is not 52 anymore because there's 1 card less in the deck. That comes out to, and if you're going to use this number, keep it really, really long. Okay, so 0.0060331825. So that's the probability of getting a queen second. See, here's the queen getting picked second, and after a king had gotten picked first. So let's put that number 0.0060331825. You see, I don't have to have the denominator necessarily there. And the probability that my first was a king was 4 out of 52. You could find out what that decimal is. And then when you divide this out using lots of decimal places, because I want to be right to at least 3 sigs. And I mean, here's even 4. Now let's compare that to getting the probability of a queen. Just getting a queen, 4 out of 52, which is 0.076923. That is not a match. So that is meaning that this situation is dependent. Yeah. And like if you go gamble in Las Vegas, they actually gamble with multiple decks of cards all combined together. And they do that because they're trying to have enough in their sample that they can then assume independence and make their probability equations easier to figure out how to keep your money. So let's see here. We see that this day's weather report calls for rain, and you make a decision about carrying an umbrella today. Compare this to a decision to carry an umbrella in general. So the probability that you're going to bring an umbrella given rain, do you think that would be the same as your probability of carrying an umbrella just in general? No. If it's going to be raining, see, I don't know what the numbers are. But intuitively, I can think of how if it's raining, I'm probably more likely to grab my umbrella than on a day when it's not raining. So I feel like this will changes probability of the umbrella. And so even without numbers, I can still make a determination that I think this is dependent or not independent situation. And that's a subjective probability there that I just did. We want to examine, are the events being male and left-handed independent? We have a simple random sample of 50 students, and we have gathered information on the variables of gender and handedness. So I need to check, will my probability of male, will it be the same when I compare my being male given I'm left-handed? And I also will want to check, will my probability being left-handed, will that probability of handedness, will left-handedness change if I know that I've only picked my males? So now I'm going to have to expand this out. So I want to get my males. So there are 23 males in all out of 50 in total. Now, when I expand out, remember that you're doing probability male and left over probability left. So, and the denominators will cancel those 50s, but the males who are left-handed are 3 out of 50. The left-handed folks are 7 out of 50. And then those 50s are going to cancel. So now I'm wondering, is 23 out of 50, which is 0.46, is that the same, question mark, I don't know. Is that the same as 3 out of 7, which is 0.429? No. So I actually don't need to do the other situation. I can already tell that it's dependent. Now, they are fairly close. And just to write out what these, the left-handedness one, being left-handed would have been 7 out of 50. Oh, and that's not equal. Not equal to, that would have reduced to 3 out of 23. So that means that we've got 0.14, which is not equal to 0.13, but they are really, really close. So like, does this result mean that there's this association between gender and handedness? Yes, it's saying that there's an association, but we can see that these things are very close. But if I was to answer just based on this data, the SRS of 50 students suggests there is a relationship, is an association between gender and handedness. Because and then I would say probability male equals 0.46, which does not, I'm going to slide this up because I'm not sure if you can see this when I'm writing, which does not equal probability male given left of, oh great, now I can't see the number, but 0.429. Okay, so, but what could fix this? Increased replication, or increased, which is just another way of saying increased what? Sample size. May help study this. Because I don't really think being male or female has a relationship with your handedness. But the data right now, I have to say that it does appear to have an association. However, if we were to do a larger sample size of maybe 100, 1,000, or what, maybe we would be able to find out if this was just chance variation or not.